Welcome everyone, and thank you for braving the extreme weather that a lot of you guys are suffering in Texas and Oklahoma right now. Luckily, I'm based in the UK, and the weather here is not too bad, so we do have power, so I think we should be okay for a while. Right, the plan today is we're going to talk about some maintenance strategies, but particularly what I'm interested in is trying to figure out what the reliability engineer has to do to recommend the maintenance activities into the maintenance planning group. And one of the main tools we're going to use for this is going to be Weibull Analysis. And immediately you say Weibull, I see people holding their hands up in the air and saying, whoa, that's way too complicated. No, it isn't. Honestly, it really isn't. Honestly, it's quite easy. That's why I like it. I like easy. Anyway, let me introduce myself first. My name is Ron. I am the head of facilities training, and I'm also the discipline manager for mechanical engineering in Petroskills. I came into Petroskills through John M. Campbell. I joined John M. Campbell in 2011, and I became the head of facilities training in 2016. I've been around a long time. I started my working life as a marine engineer with Shell. So I was actually on ships. In 1984, Shell sent me to a Shell operating company, which is PDO, Petroleum Development Oman. And I joined PDO in September of 1984. And I started my life there looking at mechanical equipment. I was a mechanical engineer. So looking at mechanical equipment, both static and rotating. And before I left there, I ended up being head of technical services. And fun time, I love Oman. I have been doing a lot of training since then, because when I left Oman, I started my own consultancy, working all over the world. And I started doing training just to support the consultancy. And what's happened now is I've actually moved more into training than I am doing consultancy. I do a little bit of consultancy now and then, but not a lot. The thing is, I've really started to enjoy air conditioning, which is really nice. Okay, so just a word of warning before we do start. The legal guys want us to put this in. All this is just saying, guys, just be practical here, be reasonable. It's a free webinar. We're not making any guarantees. We're giving you some tools to let you develop your maintenance strategies and to actually work with the reliability analysis. But please don't come back on us and say you owe us $1 million for getting it wrong, which I'm sure you won't. Okay, the objectives of this webinar. First of all, we're going to be talking about how can I document failures. In other words, what is a failure? How do I identify what a failure is? And the tool we're going to use that is FMEA, Failure Mode Effect Analysis. It's a simple tool, but it's very, very powerful. We're not going to spend a lot of time on that because that's just getting us to where we want to be. And one of the outcomes I want to know is once I've identified what a failure is and a root cause of a failure, I want to know what is the appropriate maintenance strategy to use to mitigate that particular problem. So that's one of the key outputs we're going to do. The big thing, the big focus for this webinar is Weibull Analysis. And what I'm going to try and do is to present Weibull Analysis to you in as simple a way as possible, but not too simple. What I want to do is show you how you can do it. You don't need to buy fancy software, although the fancy software does work extremely well. But Excel is a very powerful tool for this, and there is Weibull built in to Excel. Now, I don't know how many of you guys have tried to use the Weibull function in Excel, but if you're not familiar with it, it can be a little bit daunting. But I'll show you how to use it, and I'll show you some little tricks and tips. And the good thing about the Weibull analysis, that will allow us to figure out what the optimum maintenance interval is going to be if we're doing planned maintenance. And also use the term optimal. And the really powerful thing about Weibull is you don't need a lot of data. Because one of the things that people keep coming back to me and saying, well, you know, when you do this analysis of failure data, surely you need lots and lots and lots of failures. Well, if you do standard type of analysis, you do. The more data you have, the better, of course. But with Weibull, you need very, very few failures, which is good because I don't want a lot of failures. So let's get down to it. This thing about failure mode effect analysis, it's a really, really useful tool. And what it allows us to do, it allows us to look at the failure data that you have in your CMMS. And your CMMS, if it's any good at all, should allow you to output all of the failures. And so we can categorize and group those types of failures alongside either the run hours or the number of days that the equipment has run before it actually failed. So one of the things we want to do is figure out what the failures have been, but I want to identify the equipment, the component, because this works best at component level, and I also want to figure out what the function is. And you might say the function, well, that's easy. Well, I want to quantify the function. And quantifying the function, it takes a little bit more thought. It's not difficult, but it takes a little bit of thought. Now, once I know what the equipment, the component is, and I know what the equipment is supposed to do, what I can then do is look at what causes these failures. That is the potential failure modes. So for a piece of equipment, I'm going to have several failure modes. The next thing I need to know is, well, what's the effect of these failures? You know, if the effect of a failure is minimal, if the effect of a failure is the machine bleeps, I don't care. I really don't care too much. But if that machine stops and either I'm losing production or maybe even worse, it becomes a safety issue, then it's a big, big problem. And the next bit is where I'm really interested. All right, what I want to do now, excuse me, I'm just trying to get this right. Right, this thing here, the potential failure causes. I really need to do some analysis. Now, if you've done this properly, you will have done a root cause analysis on at least your major failures. A lot of your failures, the RCA is going to be quite easy, but you need to do some sort of RCA to figure out what's actually causing this failure. What I'd also like to know from you is what are the current controls? For instance, if we're talking about a bearing failure in a pump, do I already have a maintenance function in place? Am I already changing out these bearings? Do I have a lubrication schedule in place? Am I doing vibration analysis on these bearings? So am I doing anything to try and mitigate this type of failure? And mitigate, that could be either reduce the probability of the failure or even to reduce the consequences of the failure. Now, once you've got all that information, we're now going to do some quantification on this failure. It's starting to sound a little bit tedious, but you can do this fairly quickly. I'll give you an example. But what I want to know is, what is the probability that this potential failure cause will actually result in a failure? Now, it's important to link these two together. I need to know that potential failure cause. How likely is it that that will result in that failure? Now, I'm going to quantify that. If I'm using FMEA, I'm going to do that fairly simply. I'm just going to give a numeric indicator to this. A lot of the time we'll use 1 through 10, where 1 is very unlikely. 10 is absolutely certain. The next thing I want to do is, what is the severity of that failure? In that case, I've looked at this thing about the effects. And so, say, for example, if this is a fire pump and the bearings fail on my pump, it means I can't supply fire water anymore. And if that is my only fire pump, these effects could be catastrophic. So again, I want to figure out what the severity is. If we're talking about a wash pump for the maybe a domestic water pump for the accommodation block, the severity is not too bad. You might get smelly people for a day or two because they can't shower. But you see the difference we've got now in severity. What I'd also like to do is to say, how easy is it to identify the root cause before it becomes a failure? So that thing there, that potential failure cause, can I pick that out easily before the failure actually happens? Now, once I've got all that information, I can figure out what I'm going to do about it. And what I can do could be several different things. I'm sticking with the bearing in a pump because it's easy. What I could do is I could say, well, I'm going to change the bearings every 3 years. Or I'm going to do some vibration analysis. But it really depends on what this root cause is. What is that potential failure cause? And so your mitigating action should really be focusing on this. Okay, so let's have a look at a basic system. Now, again, I said I'm working on a pump. And the first thing I want to do is, because we're talking about an FMEA, I can identify my equipment. So here we've got a pump. This pump, it's got a rate of flow of 125 gallons per minute. It's pumping through a level control valve into a tank. The tank has a process requirement of 105 gallons per minute. Okay, so my pump can do 125 GPM, but the process only needs 105 GPM. Now, if we go back and we reference Nolan and Heap, who are the gurus and the progenitors of reliability, they defined failure as the presence of an unacceptable condition. And I look at that definition and I say, that's not really helping me a great deal. What do you mean? Well, they then went on to say a potential failure is an identifiable, important, identifiable physical condition which indicates a functional failure is imminent. Now, imminent does not necessarily mean today or tomorrow. It just means we can predict when this failure is going to happen, or we know that the failure is going to happen. They then went on to say, all right, functional failure. Now we're starting to get somewhere. A functional failure is the inability of an item to meet a specified performance standard. Now we're getting somewhere, guys. So what it means is, if I go back to my simple pumping system here, the function of this pump is not to provide flow at 125 GPM, because I don't need 125 GPM. What I need is 105 GPM. So we can say the pump has suffered a functional failure if it cannot provide 105 GPM. The point here, guys, is I've quantified what the failure is. So quantification is important here. Now, if we start to put this into an FMEA, and there are several methods of putting this together. This is a layout I've used quite a lot, and it works for me. So as an example, we could say the equipment is P504. Okay, the components, well, we've got a motor, we've got a pump, we've got control systems. Let's just say pump. The function, this is to supply liquid at a flow. So we've got a Q, a flow, more than 105 GPM. Okay, that's good. My next thing is, what are the potential failure modes? And I'm going to have a lot of them. So I could say a potential failure mode could be a bearing failure. I could have another one which could be a mechanical seal failure. I could have another one which might be the impeller is actually wearing out. That could be due to cavitation, or it could be due to erosion, whatever. So let's stick with the bearing failure. And for all of these, if I have a bearing failure, the failure causes zero flow. So now my flow goes down to zero. And what I can do is I can quantify the cost of the failure. And in this case, let's say that is $3,000 per hour lost production. So again, I can quantify it. And that would be the same for most of these. The potential failure causes of a bearing failure, well, maybe we've got a fatigue failure. Perhaps we've had problems in the past with lack of lubrication. So we got no lube. And again, you can just carry on going down to the root causes. What's actually causing this? Now, at the moment, you could say, all right, you've got a fatigue failure. What are you doing about it already? And it's important, you have to say, what am I doing right now? And it may be that you're doing a bearing change at, let's say, 5 years. Okay, so we know we've got potential bearing failures. That could be caused by fatigue, which could be due to end of life. But because of that, we're changing the bearing every 5 years anyway, whether it needs it or not. We then come to the quantification here. So what we're doing now is we're trying to quantify the risk. So this is on a number of 1 through 10. So the occurrence, how likely is it? Now this is where you need some past data. How many failures have you had in the past? And you might say, well, I've never had a failure at all. In that case, I'll make that a 1. It may be you say, look, these pumps, I've got a few pumps that are similar, and we've never caught a bearing. We've never changed one out in time. In that case, it'll be a 10. So maybe we'll say, all right, this is a 6. If the bearing does fail, how severe is this? This is going to depend on your process. If it's this pump which supplies water for the showers in the accommodation block, not so severe. If it's a fire water pump or if it's a process critical pump, it's going to be high. So let's say we make that a 7. What it could do is multiply these two together. In that case, that's going to be 42. Detection, again 1 through 10, but 1 is, well, I could say, yeah, I can detect that pretty easily. Because all I need to do is, perhaps I do some vibration analysis or the operator checks it, but in reality, we don't. So maybe that's a 10. The risk priority number here is this multiplied by that, which gives me a risk of 420. Now what I do is I do this for all of the different potential failures, and I quantify the risk priority number, and that allows me to figure out which of these problems, which of these potential causes I need to put in the most effort. And once you've done that, you can identify what your mitigating actions are. Okay. And this is just an example I put together, something quite simple. So if I've got a fatigue failure, that could be due to old age. Rolling element bearings are designed to wear out. That's what they do. They're not designed to last forever. So we've got a 10 by a 10 by a 9. That's a 900. I could mitigate that by a change out on a planned basis. I could also do vibration analysis. So what I'm doing, I'm trying to reduce this RPN number by either reducing the probability of the failure. And remember, this is a probability that this piece of equipment will fail in service due to this particular problem. Now, you can modify that probability by changing your maintenance interval. You're all looking at a laptop or a computer. And if I said to you, how likely is it that that computer is going to fail? It's going to have a problem with the hard drive maybe, or maybe the screen's going to go bad. Maybe the power supply is going to go bad. Now, some of you will say, well, it's not very likely at all. So it's a very low probability. And some of you will say, sometime it's going to fail. What if I change the definition? What if I said to you, what is the likelihood that your computer is going to fail sometime in the next 50 years? You're going to say, almost certain. What's the likelihood that your computer is going to fail today? Very unlikely. The only thing we've changed is the time period. So when we talk about probability of failure, that's a probability within a specified time period. Now that also means, and it implies, we can change the probability of failure by changing the maintenance interval. All right, let's get going. Now, when we talk about mitigation, we can do a number of different things. And you notice on the previous slide, just for that old age fatigue, I identified either a PM, which is either a scheduled rework or a scheduled discard. Or what I could do is I could do vibration analysis, so I could change the bearings on condition. So this is planned maintenance. This is planned replacement. This is predictive maintenance. This thing about scheduled failure finding, this applies mostly to instrumentation type failures. Things like SIS systems. So the system's sitting there. I don't know if it's going to work or if it's going to fail until I test it. So that's what we talk about failure finding. So identifying what the problem is before it actually jumps up and bites us. Just a quick word about predictive maintenance before we go on to Weibull. When you're selecting your predictive maintenance strategies, your predictive maintenance techniques, you've got a lot of options open to you. And again, I'm sticking to this thing about bearings because this is quite easy. If we talk about bearing fatigue failure, when the bearing is new, it's at 100% condition. It's good. Maybe not 100%, but certainly 97, 98%. And over time, it's good. And it maybe it might drop off a bit and we lubricate it. But at some time, you start to get a crack in one of the races. Now the bearing is on its way to failure. But to start with, that crack is so small that there aren't any technologies around that can detect it. The bearing seems to be running fine. It's not noisy. It's not hot. But what I could do, if I'm using a particular type of analysis, because we're being rather specific here, if I do vibration analysis using demodulation, some people call that peak view, some people call it SSE, there's a lot of different names, but that could give me up to 6 months warning. But it means an investment. So you invest in the technology, you invest in training for the people who do this. Or maybe you're using contractors to do it. If you don't want to spend that money, then you're not going to detect that failure at such an early stage. So maybe what you could do is you could use a really simple vibration analyzer, maybe one of those VIB pens that just gives you an overall vibration level. It'll work, but it won't work as quickly, and it won't give you as much warning as the demodulation. If you don't want to invest in this, maybe you just say to the operator, look, when you do your rounds, just get your hand on the bearing, just touch it, just make sure it's not too hot. Just be careful. You don't want him to lose his finger. But again, you've got less warning. If you wait until the bearing's noisy and the operator says, hey, there's something wrong with the bearing in P504, you might only have days before the actual failure. So this thing about the PF interval, it's going to be different for every machine, and the amount of warning you get before failure is going to vary depending on the technology that you use. Just keep that in mind when you're talking about predictive. Now, here we get to reliability. When we talk about reliability, and we went to school, we got told about the bathtub curve. And the bathtub curve, when our equipment is new, because this is the life of our equipment. When the equipment is new, we don't expect many failures, but we do get some. And the reason for that, this is often called infant mortality. This could be things like commissioning errors. We've installed bearings in there, but somebody forgot to put the lubrication in. There are maybe some problems with the instrumentation. Perhaps some of the cables got damaged. These are things generally that can be fixed quite easily. It might be a design error. Then you've got to go back to the drawing board. But once you have those things sorted out, and you get to this point here, now what you've got is a time of random failures, but low. So random, low probability. Low probability of failure. By the time you get to here, this is where we start to get end of life. This is the accepted lifetime of your piece of equipment. What we'd love to be able to do is to say, let's change those bearings right there. Just before the probability of failure starts to get so high, it's actually causing me a problem. Now, if you look at most of your equipments, very few of them follow this bathtub curve. And the reason is that most of the equipment we work with, we do too good a job. And the reason is that you already have planned maintenance. And you've got planned maintenance, you take this piece of equipment out on a regular basis, you rebuild it. So you put new bearings in, you put new seals in, you check the wear rings. If there's signs of cavitation, you change the impeller and so on. It means perhaps somewhere around about here, at that time here, that's when we've overhauled the bearing. We've overhauled the pump. And it means you never actually see this bit. So what we actually see is a failure pattern that looks something like that. So we get the probability of infant mortality every time we overhaul a pump or any piece of equipment. And for you maintenance guys, how often have you heard the production operator say, maintenance, don't touch that machine, it's working fine. Because if you touch it, every time you touch it, we always have a terrible time getting it to start again. Well, they do have a point. Even with the best will in the world, quite often we're going to have issues on startup again, and it's natural. So the point is, when should I change my actual pump bearings? Okay, we're going to lead into this. But I do want to give you a definition now before we start. A lot of people get this wrong. I've got 3 different definitions for the term availability. This is the one that most maintenance people like to use. And I don't say that in a bad way because my background is maintenance anyway. And this is the probability that the system will operate satisfactorily at any time when used under stated conditions in an ideal support environment. It does not include maintenance times, preventive maintenance. So that works. It's good for planning. It's good for planning maintenance. And if you take your mean time between failures divided by your mean time between failures plus your mean time to repair, that's what this will give you. But don't forget, you're not including planned maintenance. Achieved availability is similar, but this does include preventive maintenance. But it assumes perfect conditions. So it assumes that you're not going to wait an extra 3 weeks because the manufacturer doesn't have that particular seal in stock. Operational availability, this is real world. And this is what the operations people, the production guys, would really like you to use. So, what's reliability? A lot of you guys will be using one of those definitions for reliability, and it's not correct. Availability is a measure of downtime. Reliability is a measure of probability that a piece of equipment will not fail. Now, E. Lewis had this definition, and this comes from Nolan and Heap. And reliability is the probability that a product or system will perform its intended function for a specified period of time. So we could say integrity is the probability a product or system will stay and it will keep on working as we intend it to. And don't forget that thing about function. So we're talking about probability of failure. That means there must be a relationship between probability of failure and reliability. What we've got is this. Reliability, remember it's a function of time, is 1 minus the probability of failure. That's important because we're going to come back to that and we're going to use it again. Right, let's get a little bit into statistics a little bit. Right, this is some data we've got from some bearing failures. And what we've done is we said, how many failures have you had when this piece of equipment is less than, say, 6 weeks old? None. How many failures have you had between 6 weeks and 12 weeks? And what we start to get is just a few. As we get to older and older pieces of equipment, older and older bearings, what we find is the probability of failure increases. That's because we've actually seen failures of this piece of equipment until we reach a peak. Now, if this is a normal distribution, which this certainly looks like, then that is going to be approximately equal to the MTBF at the peak of that curve. But once you get past the MTBF, most of your bearings have already failed. So the rate of failure starts to decrease until eventually, in this case, by the time we got to about 31, all of the bearings in this population have failed. Actually, I wouldn't want to buy this pump if you're the bearings are only lasting 31 weeks. But you see the point. Now, I can change the way this looks by, instead of just taking the number of failures within a time period, what I'm going to do is I'm going to keep adding them together. I'm accumulating the number of failures. So this is exactly the same data, but this is now a cumulative set of information. So by the time I get up to 100%, all of the equipment has suffered failures. Now, the interesting thing is that because this is a normal distribution, This has given me an S-shaped curve for my cumulative distribution. Now, this is useful, and it means that this is a typical type of failure. Now, it also tells me other things. If I go back to the standard distribution, if I've got a distance between the sides of the bell curve of this, that gives me an indication of how likely is it that the bearing is going to fail at a particular age. And if I compare it to a distribution that looks something like this, this is much tighter. If I'm looking at the blue line, I really want to do my bearing change here. That's when I'm going to do maintenance. But on this one, I can go much further. I can take the risk of waiting longer to do my bearing change. So the shape of the distribution can have a big impact on when we do this bearing change. What I can also do is, what if my failures are random and they don't do this? They don't exhibit a wear out. Well, it's going to look a little bit different. Instead of this normal distribution, what I might see is a distribution that looks something like this. When's the right time to do maintenance there? And the answer is there is no right time, because this is a random distribution. So what this means is, if I'm getting a random distribution like this, don't even bother doing maintenance. It's a waste of time. At least don't do planned maintenance. You may as well wait until the thing breaks down. Because with this situation, you might decide, well, I'm going to change the bearings here. Well, if you do, you haven't really improved the situation very much. All you're doing is bringing the machine down for more and more and more maintenance. If you find you're getting a lot of failures at an early stage, that's when you're getting the infant mortality. That's probably a design error or a commissioning error. So your maintenance strategy now is going to be different depending on the shape of the distribution. Okay, right, I'm going to go back to this S-curve now. And notice what this is. This is probability of failure. But we have already said that reliability is 1 minus the probability of failure. So all I really have to do is invert this. And what I get is this. I get my S-curve, but it's the other way around. But this is now a reliability function. Now, when do I want to do maintenance? Well, you tell me what reliability you want. If you want 80% reliability, your maintenance interval should be before that time there. If you want 98% reliability, I should be doing maintenance there. So you can adjust your reliability depending on your maintenance interval. This is one of the key factors that we've got here. Okay, so now we've got the basics. We said, okay, great. What we've got is a way of identifying the failures. We've quantified the functionality of the equipment. We've quantified the risk associated with that failure. And I've identified that I can change the reliability based on my maintenance interval or my mission time. The question is, how do I really get to this data? How can I actually get something that's going to help me do this? And the problem is, statistically, it's really difficult to work with an S-curve. until my hero, Volody Weibull. Mr. Weibull, he spent his early years, his formative years in Sweden, and he was working with the Swedish Royal Navy, and eventually he moved over to the US, and he did a huge amount of work with the US Air Force. And what he did, he said, this S-curve, it's okay, but what I really want is a straight line. I don't want an S-curve. Because to get an S-curve, I need a lot of data. But if I could make this a straight line, then I only need a few data points. I don't need so many. Now, the formula for a straight line, y equals mx plus c. And even if I've only got 2 points on there, 2 points means I can extrapolate my data. It's so easy. So what he did, he said, if I take this failure data to convert that to a straight line, I can do a couple of things. And what we often do is we do a log of one or more of the axes. And that's what he did on the bottom axis, which is the time to failure. To make it work, he did a log of the cumulative failures. Now, the way he did it was rather interesting. Because, again, we've got to figure out what the probability of that failure is. And this is where Weibull really came into his own. But as you can see from this, if I can make this failure mode a straight line, because that is exactly the same data as that. Exactly the same. It's just presented in a different way. All I need here is maybe one, maybe if I've got 2 pieces of data, that's great. That's all I need. But it gets even better. Because what Weibull also said was if I look at the slope of that line, that is giving me the same sort of thing as the shape of that bell curve. If the bell curve is very tight, the slope is more towards the vertical. That means if I've got a very tight bell curve there, a vertical slope on this Weibull curve, it means that this is called the beta factor. If it's much more than 1, that is telling me that this is vertical. So more towards vertical. So my line has gone more towards the vertical. And that means if my line is closer to the vertical, I have a wear out. And that means to do planned maintenance makes sense. If my beta factor is about 1, that means you've got a distribution something like that. Don't even think about doing maintenance on this. Well, at least don't do planned maintenance. Wait until the thing breaks and have a plan for what you're going to do when it does break. That might mean keep a stock of seals. Make sure your guys are familiar with how to change a seal in the field very quickly, because it's pointless doing these replacements. If your beta factor is less than 1, you've got infant failures. Now that means you've either got a design problem or you've got a commissioning and installation problem. And that means the strategy you're going to use is going to be very different to these other 2. Now the other factors that Weibull used was ITER, and that is the scale parameter. That is where the cumulative probability of failure is 63.2%. That's because that's the exponential of -1.632. So what I can do is, if I plot 0.632 on here, and I come straight down to here, that is my characteristic life. Help if I could spell. That's my characteristic life. And we're going to use this in the calculation. A lot of the time, this is going to be close for a normal distribution. This is going to be close to MTBF, which is round about here. Now, there is a third term in there, which is called gamma. Gamma is well, there's three different types of gamma. The one we're mostly interested in is that time where the failures start. So let's say you've got a gamma 1 of, let's say, 5,000 hours. That means for the old equipment you've used and all of the history that you have, none of these things have failed at less than that many hours. That's all gamma is. It's a starting point. So what we get is beta less than 1. This is my infant mortality. Beta approximately 1. This is useful life. Beta more than 1. That's my wear out. That means I want to be changing or doing my maintenance in that sort of area. Okay, so now let's do this in Excel. What we're going to do is convert the failure data into a suitable format. The first thing we do is sort the failures from the smallest to the largest. That's this guy. So it's just sorting, doesn't matter. Then what we do is we rank this. So this is just a simple method. We just say, what is the item number of this? Item number 1, item number 2, item number 3, and so on. To get our vertical axis, we're now going to convert that rank into a median rank. Now, there are several ways of doing this. The one I use is Bernard's, and that is I minus 3 divided by n minus 1. I, that is just the item number or rank. N, that's just the total number of entries that you have. So you do that calculation. Again, we can do this in Excel. Nice thing about this is it always goes from 0 to 1. Now, because we're talking about failure data, we're going to invert this, and what works best is 1 over 1 minus the median rank. And then what we'll do is we're going to take the log of that. Remember, this is what Weibull's genius identified. If I take a log and put that on the vertical axis against the log of the run hours, so these run hours here, that's these things. I now plot this on the x-axis and this on the y-axis. And this is what we get. And I did this in Excel recently. So exactly the same data here. Notice this is the log of the run hours, and that's in green, so that's my x-axis. And that is my y-axis, and I do get a straight line. Now, this is your first test. You look at this, and if everything is close to the line, you have a good sample of data. If you've got some data over here, they're outliers. And if you've got outliers, that means you've got more than one failure mode together in your data set. You don't want that. That means you need to be more analytical about which data you're using here. Now, once I put this data into Excel, what I did was I just plotted the points, and then I said, put a trend line in there. Once I've got the trend line in, I also say, show me the calculation, show me the graphics. And Excel does this automatically. That number there is beta. So immediately I look at this and I say, wow, this has got a beta of 2.1879. That's more than 1. That means I can actually I can assume a wear out. I can do my maintenance interval at the right time. This is the crossover. Okay, I'm going to use these two together to calculate eta. What I could do is I could use this directly in Excel, and I could use something called linest. So linest, so at linest, and this is a line estimator, and this is my y-axis data. This is my x-axis data. I use true and false to get a good number out of there, and it gives me my beta factor as a number. And that's something I can pull out of Excel and use it anywhere else automatically. My intercept, minus 21, which is what's showing here. My intercept is at index linest, and again, that's my y data, and that's my x data. And now I can calculate eta by doing exponent, and that is simply these two, beta and intercept. So that is the exponential of the intercept divided by the beta. Okay, so what does it mean? Well, what it means is, if I go back to this a moment, it means by having just a few points of data, I've calculated what my actual beta value is. That's helping me decide on my maintenance strategy. I've also got some other values here. And that means I can calculate what my reliability is going to be for a particular mission time. And for mission time, think maintenance interval. So it means I do my exponent, the mission time, minus gamma. Usually we're going to set that at 0 unless you know for sure you've got something. Eta we've just calculated to the power of beta. And honestly, guys, this thing works. So what we're going to do now is, now we've got this basics, we can calculate the reliability of a system. Don't forget, every machine's a system. Once I've got my probability of failure, multiplied by the MTTR, mean time to repair, that's going to give me my downtime. That means I can calculate my availability, and I can optimize that and work with production to make sure this is acceptable. This is what they need. Now, I'm not going to go through all this, but remember, you can have multiple components, each with their own reliability, and you can put that together and you can calculate the overall reliability of a piece of equipment, whether that's going to be a series machine or a parallel machine, or even a real world where you got multiples. As I said, I'm not going to spend time doing this. That's for a different topic. But what I am going to do now is just going to finish off with a little example. And this just takes me back to my time actually working in an OPCO. The production planning department have told me this particular compressor, well, it's got a design flow of 73.2 million scuffs. The availability we need for next year to achieve our production targets is 96%. Now make sure you know which availability they mean. We know from our maintenance records that the mean downtime, which is the MTTR plus logistics delays and so on, is 489.3 hours. So the number of failures in 1 year, which I'm allowed, is whatever the uptime is, or sorry, the allowable downtime divided by the MDT. So that says 8,760 hours in 1 year. That is my probability of failing divided by the 489 hours. And what I get is a 0.716. And I can calculate my MTBF from there. So the probability of failure in a year is this, which of course is this. That means my reliability I must have is 1 minus 0.716, 28.4%. You think, well, that's not very much. What I could do is I could calculate my failure rate, and you can use the Weibull function in Excel by doing this, and I'll show you an example. So what we do is we can calculate this failure rate using the Weibull parameter. If I've got my failure rate, then reliability equals 1 minus the failure rate. That gives me reliability for a particular run hours, or this is emission time. So this would be the time at which I expect to do maintenance. So what we end up with is an S-curve from our failure data, and you decide, well, when do you want to do maintenance? Well, at 28.4%, that's going to tell you, well, it's going to be about 17,500 hours. That is your optimal maintenance time based on a 96% required availability. It means that your reliability depends on what the production guys need. And you can twist and turn that reliability number by twisting and turning your maintenance interval. If they want a higher availability, that means a higher reliability. That's going to change your maintenance interval. This is the way we should be developing our maintenance schedule. So, just to finish off, I've gone longer than I expected, but it's still an hour. What have we learned? These are our key learning points. I can use a formal method to identify the failures in the failure modes, FMEA, FMECA, LCM. My reliability stats work best for individual components and individual failure modes. Don't mix them up. Determine the maintenance strategy based on your Weibull shape parameter. Yep. Work with your production needs to reconcile the availability, the reliability. And I don't need a fancy, expensive software. Now, let me show you where I got my data from. This is a spreadsheet showing exactly the same data, and I pulled the graphs from here. So these are the run hours to failure. I've ranked them here, and up here you can see what the calculation is. Remember, I minus 0.3 divided by n plus 0.4. That gives me the median rank. I calculate 1 over 1 minus. I do a log hour of the run hours. I do a log of that 1 over 1 minus the median rank. And what I'm doing is I'm graphing these two. So if I plot this data, hopefully. Yep, there it is. So there's the data I'm using to plot this graph. This failure rate up here, this is Weibull, and it's B4, which is the run hours, times beta, which is what we calculated here, and eta, which we calculated here, and true, just to get a full number. And that gives me my failure rate. My reliability is simply 1 minus that. And all I've now done to get this S-curve is the run hours against the reliability. And if you wanted to, you can calculate the mission time based on required reliability, punch your reliability in there, and you get the mission time here. Little bit of work to do the spreadsheet, but once you've got the spreadsheet, it's pretty easy. Okay. So, we're done. We're finished. And I know this was a fairly rough and bumpy journey. It's pretty quick. This information was all taken from, it was all taken from REL5. In fact, I think I mentioned it on the last slide. It's sourced from REL5 process plant reliability and maintenance strategies. So what we do is we build this spreadsheet in the course. And I found it very, very useful. I use it a lot. It's not the only thing we do, and if you want to concentrate on the webinars, in 2 weeks, Jerry Ross, our Senior Reservoir Engineer, will be hosting a webinar entitled Building Your Resilient Oil and Gas Career. 2 weeks after that, because we're now in a 2-week cycle, and this is going to be based on simulations. My new hire engineers have a lot of theory training, but no operation sense. How can I instill practical operations control and safety sense to new hire engineers? Honestly, guys, these are really great webinars. We have many other titles down there. We have not scheduled them in for a particular date yet, but let me know which ones you prefer, and we're happy to work with you. This is our instructor-led training. We've got ME44 and ME41. They're coming up. We said November, actually. It's coming up in March, the next one. And if you've got any needs, feel free. There's my email up there. Just drop me a line, and I'll be more than happy to help. Okay, Clay, 3 minutes over, and now it's going to be half an hour.
No problem. Good stuff. Yeah, we do have a few questions here, and then we'll have time for a few more. So if you still want to get a question in for Ron, you can go ahead and type that into the chat or the Q&A. So we had a couple of different questions that came in about specific components and how this method worked for those. So the first one asks, is it possible to use this method for pipeline integrity?
Oh, yeah, sure. I mean, I was using this for rotating equipment, but you can use this for any sort of equipment, any sort of failure, as long as you can group those failures together. If you've got similar failures, such as corrosion, perfect. I've used it a lot on heat exchangers for figuring out when's the right time to change a tube bundle. And so if you decided to use this for corrosion issues or pipeline, that's probably your biggest problem. But yes, you can use it. And if you find that you've got different parameters from area to area, if you want to get a tighter distribution, you might do it in certain areas. So say a mountainous area might be different to a plains area because you've got different types of corrosion issues. But short answer is yes.
Okay, and the end of that answer kind of relates to the next question, which is if we can use Weibull for data from a set of identical pumps.
Oh, yeah, really. Yes. It sounds too good to be true, doesn't it? But yes, it does work really well. The caveat would be if the pumps are working in a similar type of environment. Say, for example, where it would not work, if I've got one pump which is working in the North Sea platform, and I've got another identical pump which is working in, let's say, the Arabian Gulf. Because the environment's drastically different, the failure modes could be different. But if you've got a set of pumps, let's say in a refinery or in an OPCO, which are in similar environment, then yes, it works well. In fact, the more data you have, the more accurate it's going to be.
All right. The next question, to paraphrase a little bit, it asks to compare Weibull distribution to other fitting distributions like log normal, for example.
It's a little bit different. Really, when we talked about the types of distribution, a normal distribution is just a bell curve, and that's used within Weibull. So the way I tend to think of it is that Weibull is a level above several of the other distributions. They can handle many of those distributions. And in fact, a survey some time ago said that it's more than about 95% of failures adequately fit this Weibull pattern. So it's think of Weibull as being a collector of the other types. So it's not better than one or the other, but most of the others are integral to the Weibull.
Okay. Another question asks, is it preferable to use 20 set of failures to minimize the area, or I'm sorry, to minimize the error?
The error. You know, that's what I used to do. When I was using standard types of data analysis before Weibull, I would try and specify at least 20 because I want lots and lots of data to actually give me a good answer. But the beauty of Weibull is you don't need that. I didn't really address it in the webinar, but one of the problems that you're going to come up against is that when you get a piece of equipment, you're going to have many types of failures, and you're not going to get 20 failures of the same type. And that's why we've been forced into using things like Weibull. The problem is once you start using failures from different root failure modes, then you're twisting the data and the data's being deformed and it won't tell you as much. With Weibull, because we're using that straight line, then as long as you're fairly confident that the failures are based on a very similar type of history, then it will fit a straight line. So, 2 failures is great. In fact, if you make an assumption your failures are random, which is it's a bit of a leap, but you can do an adequate Weibull analysis with 1 failure. And it actually works reasonably well. Of course, the more you have, the better. But any more than about 3 or 4 is you don't really need it.
Okay, and then we have 2 more here, unless any others come in while we're addressing these. Next question asks, how do we incorporate maintenance activities in this data?
When we say maintenance activities, I'm going to presume that you mean how do I incorporate this into the maintenance schedule? I'll carry on like that unless you come back and say something different.
Yeah.
The way this tends to work is the maintenance group don't normally decide when to do maintenance. They will make a schedule, but say for example you've got a pump. Do you do a major overhaul at every 8,000 hours, every 16,000 hours, and so on? That information should be coming from the reliability group. So the reliability guys will look at the equipment, will look at the failures, and they'll say, look, for this type of pump, you should be doing an overhaul every 3 years. And that is what should be input into the schedule. Now, the maintenance activities and the detailed maintenance plan, that should be coming from the maintenance people themselves. So in that case, that's how I would integrate them.
All right, and then last question here says, is Weibull analysis suitable for complete trains?
Oh, not really. When I do Weibull analysis most accurately, what I prefer to do is I prefer to split it out by component and by function. And that means for a fairly complex piece of equipment, you'll be doing a lot of Weibull analysis. The reason why you see this data sometimes on a complete train is because the manufacturers want to give you a nice warm feeling about their equipment. So they'll tend to give you an MTBF value for a complete piece of equipment. In that case, it's okay for comparing one type of equipment against another. But as far as Weibull is concerned and developing a maintenance plan, it's not really a good idea.
All right, and one last question slid in here during that and asks, can we consider the mechanical seal and its flushing line as 2 items in the series?
Yes, you can. Because if you can identify what the failures are on each one, and you can analyze them separately, and I'm assuming you've got things like the flushing line being plugged or the flushing line cracking, then you can identify what the failure modes are, and you can assign a reliability to that, or you can calculate the reliability. And then the seal itself, again, you can identify what the reliability for that is. The two of them in series, then you multiply the reliabilities together to get your overall reliability figure. So yes, that would work. Just be careful about separating the items out.
All right. Well, thank you everybody for the excellent questions, and Ron, thanks so much for this presentation.
Well, thank you very much everyone for staying on, and I hope it's useful. And don't forget, you've got my email. Drop me a line. You can find me on LinkedIn if you'd like to get in touch that way. But we're here to help.
All right, and as I mentioned, we'll make sure and send out the recording and the materials in the next day or two once we finish processing and cleaning those up. So make sure and watch out for that. And thanks for spending time with us today, and we hope to see you in future webinars. Stay safe, everybody, and take care.
Thank you very much. Thanks, Clay.
All right, thanks.